Wes Hardiker joining us today. I'm Dave Zawatson from UCDavis, and we also have Shannon Chi as a co-host. So I asked Wes if he would be willing to, kind of redo one of his presentations on DNS Sec that he's done in the past and present to us. And that's how everybody ended up here today. So this is intended to be sort of a DNS Sec overview to give you an understanding of all these nuanced interactions. And with that, Wes Hardiker.
And thanks for having me too. This is a topic near and dear to my heart, and I've been advocating DNS Sec for many years at this point. I will go into the depth of, you can actually run into problems, when you have interactions with your parent, regardless of whether it's DNS related or DNS Sec related. But quick background, I'll give it a little bit about me, not long. I'll go about some DNS background. I realized with the growing audience size that there may be people of various skill levels. So we'll start off fairly high, and then we'll get into comparing DNS security options, and then the real nitty gritty with geeky stuff will happen will be the predominant part about how DNS Sec actually works, and we'll end with some recommendations and leaving a lot of time for Q&A. So if you have questions, we'll deal with them at the end, but please do feel free to ask anything at the end. For me, my background is I graduated from UCDavis. I have a master's from the electrical engineering department, and I worked for a number of departments, both as a student and then for a number of years afterwards. I meandered around, always doing security-related research. I'm currently a computer scientist at the University of Southern California's Information Sciences Institute in our Networking and Cybersecurity division. I do a lot of stuff related to intrusion detection and general protocol security. I've done a lot of internet standards work, including DNS specifications, including some of the specifications we'll talk about today. I'm currently a member of the Internet Architecture Board that will have been for about 3 years. I'm the operational manager of b.rootservers.net, which is run out of ISI and has been since the creation of the DNS. And then I'm also a member of ICANN and the Root Server System Advisory Committee as a representative of our root server. The Information Sciences Institute, real quick, we do a lot of stuff. We're actually very, very spread. We have an artificial intelligence section, a computer systems and technology sections. I'm part of the networking cybersecurity section. And for those folks from the EE area, Moses is actually still what UCDavis, I believe, is using to do chip fabrication. That's been run out of ISI for about 30 years too, which I didn't realize until after I got there, and my advisor at UCDavis reminded me that we actually had a connection way back when he learned I got a job at ISI. So first, I'm going to go into some DNS basics, in part because I think most people realize there's lots of this, but the complexity of what goes into even opening a simple website is often misrepresented. So most people actually just see the web as, hey, I open a browser and it goes and talks to some server and then you're done, right? They have no idea about Amazon Web Services and all the other complexity that goes into hosting websites. And they don't know about the DNS in general. The technical people tend to know better, right? They know that they have to go ask some resolver for, hey, where is that web server? And you get an answer back. And then you open the HTTP connection and you're done. The reality is that DNS is much, much, much more complex than that. Even though the protocol is simple, there's so many boxes that come into play because you end up talking to the root servers and then to the com servers and then to example.com, and you have a ridiculous number of resolvers that you might be dealing with that might be caching information, which is part of why today's discussion is happening. There's resolvers at ISPs, there's resolvers in cloud providers like Google and the quads, as they're well known. And even your home router is often caching information as well. So my demonstrations for the complexity level of this is the IETF runs a example.com webpage that is, example.com is just a domain that's supposed to be used in documentation. And there actually is a webpage there saying this domain is generally useless except for documentation. And so there's these little graphs that I created about 15 years ago, actually, when we were originally talking about how to demonstrate DNS Sec and how much it's used. Each line in this is a DNS request. So there's the client, which is one of my laptops, is right here, making a request to a resolver. And this is when you go to that web page with a resolver with no information in it. In other words, there's nothing in the cache. All of these lines end up getting created. If you go to a slightly more complex example with IETF.org, actually has some other graphics and other stuff in it. Maybe they're loading JavaScript. I didn't actually look into all the details of what's going on, it gets much more complex. And then while I was making the most recent versions of these graphs, I asked my colleagues at ISI, I said, what website do you think is the most complex with respect to advertising and has the most junk on it? And the winner was WebMD. And WebMD has a ridiculous number of DNS requests that get created by loading just one web page from a completely empty resolver. And this is crazy, right? How many requests it takes, and most people don't realize this level of complexity. So what do resolvers do? They do all the hard work for you. Again, we go back to the example of my laptop sends a request to a resolver. That resolver is responsible for querying the entire DNS tree in order to find your answer. And the thing is that they also remember that answer for a long period of time, so that after they ask it once, they won't ask it again for a while. And we'll talk a lot about that today in caching. And there's lots of different types of resolvers. I indicated before, they're in ISPs, they're in cloud resolvers, they're in your home devices. There's stub resolvers, which actually run in applications, and lots of different types. I'm not going to go into the details of many of those today. If we actually look at how the DNS is structured, there is different parts of it. There is a root, which is at the top, and it delegates, everything below .edu due to their servers. So a different organization is responsible for running edu, and then UCDavis is responsible for serving data out of their own part of the tree. So there's this whole delegation system that works from the top down. That works really, really, really well. It was designed to be a very distributed database, but there's a few things that have to happen. They have to have information in both the parent and the child in order for things to be to stay in synchronization. So UCDavis, for example, has 3 name server records, DNS 1, 2, and 3, and both the parent and the child have to have those in sync. And that happens because the parent has to be able to tell a resolver, I don't know where UCDavis is. I don't know all the details of what's inside UCDavis. I just need to tell you where to go in order to find that information. And that happens from the root on down to basically these links saying, go forward and here's the rest. And also in sync has to be the cryptographic DNS links that we'll talk about later. The child is authoritative. The child is the one who supposedly has the right answers. So the child is the one that you should always believe. And if that cryptographic link is broken, then you end up with a problem. But you also end up a problem if any links are broken. So what happens when things don't match? So in this case, there is, maybe the edu has DNS1 and DNS2, and somebody's added 3 and deleted 2. And if they don't match, it tends to work still if there's at least one thing that is matching. And that's actually true for the security side of things, as we'll see later too. But it's going to slow clients down because they end up having to, in just the name server case, they might try and go talk to DNS2 first, and that doesn't exist or it doesn't respond. And that becomes what's known as a lame delegation, a terminology that I don't think is very descriptive, but it's stuck in the world. It's all over the place. And then, eventually the child will actually return, actually, that's not my name servers. 1 and 3 are my name servers. And it actually turns out that there's different resolvers out there that will believe, some will believe the parent and some will believe the child. I actually wrote a whole academic paper on that subject. And unfortunately, many, many, many zones exist with lack of perfect synchronization between the parent and the child. And so it's easier to see when DNS Sec is enabled because things actually hard break, which is sort of what the worst case situation. But you end up with a lot of slow stuff. The Internet Archive actually had an issue a while back that I helped them fix because they had name servers in the parent that didn't match the child, and it was making the Internet Archive load slower, to be perfectly honest. So everybody can end up having it. But when you add security records, those must match too, and that's the big takeaway. So here's my rule of changing data. You should always remember that probably 90% of the time you run into errors, they're probably from mismatches or often cached mismatches where resolvers have information in their caches that they have remembered, like one of my previous slides, right? Resolvers remember data for a long time. And if you don't remember that as you're changing data in your zone, you will get into trouble. And 90% of the time, that's where errors occur. Sometimes it's also because people make bad mistakes in the data itself, of course. And so my general rule of changing data is add new records, then wait, publish stuff to your parent, regardless of whether it's NS records, whether it's glue records, address records that you have to go along with your NS records if they're in zone, and then DNS Sec related information. Publish them to your parent and then wait. Then remove the old records from the parent and then wait, and then remove your old records. So all of those steps don't need to be perfectly done. And the wait time, that I have listed down below, there's actually much better math than this. But if you just think of it in this simple fashion, this works pretty much all the time. And so the wait time is 2 times the maximum of your TTL and your parent's TTL, and they can differ. And I meant to actually put in a slide with real differences for UCDavis, but as an example, for the name server records in Edu are likely longer in TTL than the name server records in UCDavis, or at least that's the common trend. TLDs tend to have very long TTLs, and you don't get to control them, they do. So you have to wait for that length. And the 2x is a little of a misnomer. It's actually, somewhere over 1 because there's a delay in propagation and everything else. So 2x is the safe value, but you could probably do 1.1 or something like that. So let's actually look at a couple of DNS security options. I'm going to talk about 2 different types. So why do we do it at all? Well, cache poisoning is the big reason. Most people have heard of this problem before, where if my laptop asks a resolver for information, my resolver has to go do all of that querying to fill in all of the possible answers and talk from the root on down. And if an attacker, actually gives that resolver an answer fast enough, it'll actually win. And the reality is, without any form of security, the first answer always wins. The DNS will believe the first answer and just ignore any others. So that's obviously a bad thing. So, and the nice thing is that the resolver remembers that answer for a very long time. And note that the attacker actually can set the TTL for that answer. They can set it to a month. And then you end up in trouble for a month until that resolver's cache is cleared. So the easiest, and I'm not going to go into great detail in the next couple of slides, but the easiest types of attacks are you ask for www.example.com, and old code used to believe not only that, but if you put any information in the additional section, just extra information that goes in the end of the DNS response, it would believe it. So you could put in totally unrelated information, like your bank.com is at some bogus address, and it would believe that and remember it. These days, resolvers no longer do that. They're actually trusting to make sure that they go to the right source in order to get information. And then there's also, you can just sort of flood a resolver with a bunch of answers. And if you can properly guess some random, typically random information in it, like the source port, for a long time, people were using a source port of 53. So that made that really easy to guess. Nowadays, there's both an ID field and the port number that if you combine those 2, you should get a decent amount of security just from being able to overwhelm that random guessing. So these are sort of the things I just talked about, a couple of them. The resolvers have to do a bunch of stuff to make sure that things don't go wrong. The real end result of this is just doing all of the rest of these isn't cryptographically strong. It's still possible for on-path attackers, that can see and copy and edit requests and generate a response to break things. So at the risk of getting a song stuck in your head for anybody that's a parent, can we fix it? Yes, we can. Bob the Builder would be proud. And really quickly, I'm going to narrow our scope today down to sort of the right-hand side of this diagram, because if you look at how DNS data is published, your zone data starts somewhere, where you're the zone owner. In this case, I think I put IETF.org on this chart. You publish it through registrars, which then go to the registry, which actually is like PIR for .org. And that information eventually is used by DNS authoritative DNS servers to actually serve it. And it's queried all the way down to recursive resolvers like and end users and applications. So today I'm really going to talk about the right-hand side, right? From the authoritative servers on down. I'm not going to talk about the registration side of things, even though we are going to talk about putting new records in the TLD zone. But do note that attackers get to pretty much, they target all of this, right? The social engineering attacks of taking over domain names and registrars happens just as much as trying to mess with the data on the right-hand side. So there's actually 2 different data protection mechanisms. There's sort of object security, that's one approach. And then there's path security, which is sort of the different approach to protecting DNS data on the fly. Object security is DNS Sec, and this is what we're going to spend most of our time on today. It's protecting the signatures themselves, the actual records, and it's using public and private keys, standard, public-private key cryptography in the same way that, PGP and things like that use it as well, which you're probably potentially familiar with. The important thing is that it's signed by the owner. So the person that actually creates the data signs it, and it's verifiable anywhere. Once it's been signed, you can match the signatures to the data and they either validate or they don't. But it only provides integrity protection. It's not like PGP where you can encrypt. It's only doing verifying that the data has not been modified in transit in any way. Provides no privacy protection. Path security, which I'm sure most people have followed, lots of discussion on the internet around DNS over TLS, DNS over HTTPS, and then eventually, not too long from now, I'm sure there will be DNS over QUIC. In fact, I know there will be. And it really tunnels answers securely between 2 points and your requests. But it provides point-to-point security, and it really only helps you from one point to another. So you have to trust the person that you got it from and trust that they got it from an authoritative source, and that actually can make it kind of complex to get deployed all the way out. So what are the differences? Object security provides end-to-end integrity, as I mentioned, without privacy. And it's a very distributed trust model and requires no real massive configuration. The resolver that's actually doing validation only needs to know about one trust anchor and it's done. It's typically not deployed all the way to the user, though, which is known as the last mile problem. Your laptop doesn't likely run a DNSSEC validating resolver, though I wish they all did, but that's my personal viewpoint. Path security, on the other hand, provides point-to-point integrity and provides privacy. It actually encrypts it, which is what has been talked about a lot in the last couple of years. But it doesn't actually verify that the data came all the way from the origin. It really just sees, did I get it over this link properly? Is there any person in the middle that might have gotten in the way? And the problem with that is that deploying it means that every link everywhere must be protected and trusted with no bad parties, anywhere in that chain. So that's its weakness. But it does solve the last mile problem, which is really what that has been pushing toward is encrypting things between your laptop and your ISP's resolver or the cloud providers. And they're actually the ones driving it. They have many complementary properties, though. So if you think about it from the point of view, do you have to pick one or the other? Well, no, actually, it turns out that they both work really well together, and there's good arguments for wanting both at the same time. So you can put your locked object in an encrypted tunnel, and that's actually provides you better security than picking just one or the other. So they're stronger together. They sort of provide both the integrity and the privacy protection. It fixes the last mile problem. It fixes all of these problems that I've talked about. There's a bunch of documentation related to them. These are all the IETF RFC numbers on the right-hand side that talk about DNSSEC. There's actually a huge list there. I couldn't list them all. And then all of the other ones, DNS over TLS and DNS over HTTPS being the big common one that's talked about these days is 8484. DNS curve is sort of an early one that sort of is not really used as much, but it was another point-to-point type solution for resolver-to-resolver communication. Resolver to authoritative server, I should say. So where are these protection areas used? As I mentioned, the tunneling is occurring really on this left-hand side. This is where its power has really shown, whereas DNSSEC is used between the resolver and all of the authoritative engines that are around the planet serving data. It is possible to use them in the opposite place, but using each of these in the opposite location requires a massive amount of deployment. You'd have to encrypt all of the links in order to use the tunnel-based ones on the right, and you'd have to get validating resolvers in every device in order to use it in all the ones on the left, and that's sort of hard to do, and most people don't think that's easily accomplishable. So now we're going to dive into DNSSEC itself, and as I said, this is the brunt, and this is where the geekiness really starts. We know all of this type of stuff. The one important element that I want you to take away is that if I sign something in example.com, if I make this record that exists in example.com, it doesn't matter whether it goes to ISPs or the cloud or to your home router or to your laptop. It doesn't matter how it got there. It's just fine to be over a laden swallow as well. The object has been signed and cannot be modified, even if it comes on a skateboard to your front door. That's its true power. How does it actually work? Well, first off, the resolver has to have one root public key to start with, and it has the public key of the root of the DNS. It only has to know that, and it can chain everything else from there. So it does that by stepping down this tree where the root's DNS key, and it's the very top that we won't talk about that rolling aspect today, but it's its own level of complexity. There'll be one chart that kind of hints at it. But it signs a record which is called a DS record that is part of the edu zone, for example, for UCDavis. And that DS record is a secured cryptographic hash that points to the edu zone's DNS key, so that you know that you got there properly. And the signature on it shows that the root zone promises that this is the right DS key for the edu zone. Similarly, the edu zone has a DNS key of its own that points to the DS record for UCDavis and says, this is the DS record for UCDavis, I promise. I'm cryptographically signing it to prove it. And the DNS key for UCDavis can then be used to sign any of its records internally. So you get this very secured chain all the way from the top to the bottom, with the resolver only having to start with one cryptographic key. There are opponents out there that actually think that this is actually a problem, that they want more keys like the certificate authority that's used in the web industry. I won't go into that level of politics, though. In the end, the resolver actually returns this bit, this AD bit in the final response packet back to the client and says, all's good, I verified it all the way top to down, right? And there's a bunch of other mechanisms I won't talk about too much, like how to detect when you're entering a zone that isn't secured and things like that. There's a lot of components of DNSSEC. There's various types of records. There's DNS keys, which are, what I sort of talked about, the public key half of your public-private key pair. The private key is not released. The DS record, as I just said, is sort of a link to subzones, child zones, DNS keys. There's a CDS record, which I threw in there. I'm not going to talk about it today, but it's sort of, if you had a lot of zones that you were managing, you'd want to use this. If you're just only signing one zone, you probably use your registrar's web interface or something like that to update DS records. CDS is sort of an automated way of doing that for large carriers. RR-SIGs are the new DNS record type that actually signs and is the signature data on the rest of the data of that type. The important thing is that it signs triples. The class, so internet's really the only class in use in the world, with a minor exception for chaos in a couple of places. The Q type, what type of query am I doing? Name server, an A record, a quad A record for IPv6. And then the Q name, oops, I have class on there twice. And then so Q name being the actual name. So you send out, resolver sends out a query for, I need the name servers for UCDavis.edu, and the RR-SIG signs all of the records. And that has an important property to it, that if any record in that set is added or deleted, then the signature will no longer validate. So you actually know that you got all of the records back, not that just a particular record is correct. NSEC proves that there aren't stuff between two names. So if you have an NSEC record that is between your Apple host name and your Orange host name, positively that banana can't exist, because an NSEC says there is no word in between that, lexicographically speaking, that is. And then NSEC 3 is a hashing version of NSEC. Generally don't use it. There are reasons that people need to. You're probably not in that camp. Ask me offline sometime if you really want the details of that. So what is the real world view of what all this stuff looks like on the wire? This is, so DIG, as I think many administrators know, is a tool for actually doing DNS lookups that comes out of the bind utility. The not utilities have something called KDIG. There's other tools that do this, but DIG is sort of the most famous. And this is really saying, I want the name server records from UCDavis.edu. Here's the answer, and here's a whole bunch of additional information. The AD bit, and this comes out of my local resolver, is actually validating, and the AD bit says, I validated all of these results, and this is the truth, at least in the answer section. The other big thing that we'll talk about a lot today is the TTL value, which is this field sort of in the middle, which is how many seconds are left before the resolver's cache decides I need to query again, all that infrastructure again in order to get the information. In this case, it's over just under 10,000 seconds. When I turn on DNSSEC, and I ask the resolver, hey, I want that same information, but also please give me all of the cryptographic junk that goes along with it, you get some extra records back, and you get these RSIGs back, and then you get RSIGs in the additional section as well that signs the A record, as I mentioned. Breaking these down a little bit, the RSIG actually signs a particular record type that I mentioned, plus the name, which is on the left. So the type is name server, the name is UCDavis.edu. That combined with IN, which is an internet record, is again the only thing people use. It was signed by a key, and there's this hint that I won't really talk about the math behind it, but it's just a really quick mechanism for if you have 5 keys to look at, it helps you, instead of having to do cryptographic checks on all of them, it helps you find the right one quickly. But even if nothing matches, you're supposed to go do cryptographic checks on all of them anyway. There's a signing algorithm. So what algorithm was actually used to create the signature? There is a end date. This is the length of which this data can be replayed by a resolver. This does not mean how long you should cache it. Remember that the caching length, the valid caching length is over here on the left, is 9936. The signature date means the signature will be considered good for this long. In this case, it ends in 2023 in January 6th. The begin date, in other words, you shouldn't be using the signature before that time. It's really rare to get a signature that is beyond now. That really means somebody has messed up publishing somewhere. And then finally, there's all the cryptographic junk. I've truncated all of these because they wrap on the screen a few times over in order to get all the data on there. So there's lots of dots in these slides in order to make them fit. Looking again, we can actually query just for the keys themselves. Remember that all of DNSSEC data is actually stored in the DNS itself. So I can ask UCDavis, hey, what is your key? And then you get this gobbledygook on the right-hand side, which I've truncated quite a bit. And you also get a few other bits of data in these that are important to know about. So the 257 and 256 are the type of keys in use. There is a zone signing key, and that's the ones that have a 256. The 7, that one bit at the end, really means secure entry point is what that bit stands for. But the zone signing key is designed to sign all the records in the zone. So it signs all your A records, your quad A records, your mail server records, all of the records. The key signing key, on the other hand, its only job is to sign the keys themselves. So it's like a entry point where you say, I'm going to use this key to sign the keys, and then this verifies that the rest of the keys can be used to sign anything. So it's a double stair step, and we'll talk a little bit about why we want to do that on the next slide, I think. Oh yeah, one other quick point. The DS record is that we talked about before is typically done on the KSK, and it's the one you're actually going to give to your parent to say, this is my key signing key. This is the one that all people coming at me should point at in order to verify anything below my tree. So why does DNSSEC have 2 key types in the first place? A lot of that is due to history and how different providers need to separate out the operational practice of running a zone versus the person that actually owns the zone. And there's not many great examples of that. The root zone is a fantastic example, because the zone signing key, the one that is allowed to sign all of the records, is owned by VeriSign, which is contracted out. The key signing key is owned by ICANN and IANA, the people that actually are responsible for owning the contents of the zone. And they can, give a new zone signing key to a completely different publisher if VeriSign failed for some reason. So the owner of the zone has the KSK, and the actual operator gets the ZSK. That's one reason for doing it. Another reason is that the zone signing keys are designed to be rotated frequently, so that you can use smaller keys, which allows smaller packet sizes in general. Signatures are smaller and things like that. It's very easy to roll them. It doesn't require you to communicate with your parent in order to change information at your parent, so that whole synchronization issue goes away. And software today completely automates this. There's really no reason that you should be doing it manually to roll ZSKs. And you can roll them frequently. It really shouldn't matter that much if your software is good. which most modern software is, or providers, I should say. The KSKs, on the other hand, as I said, the DS records need to be pointed at your KSK from your parent. It's harder to rotate them because you have to communicate with your parent. We'll go over that in a minute. They're often longer in size. So the keys that you typically see are 1024-bit keys for RSA for sun-signing keys and 2048 bits for KSKs. And in order to roll them, it requires some special consideration. Note that you can actually have just a ZSK. You can actually just have a key that the parent DS record you can give to your parent that says, you know what, I only have one key. Just point to this and I'm going to use it for everything. Most software these days takes the approach of using two keys. Most of that actually probably comes to history more than need. So this is the example of, okay, well, if we take all of that I just talked about, you have DNS keys, for UCDavis that are in your zone, and your parent, if you ask your parent, which is the at part of this, is I'm asking the edu servers for the UCDavis DS records. I'll get a response for here's a DS record, and here's the key lookup hint for which key you should be looking up in the child zone, and then there's a hashing type for what is the hash that actually verifies against the key that I'm running a hash against. SHA-256 is the one that everybody should be using. Generally, you don't even need SHA-1 anymore, and it was replaced years ago, and there's nothing that doesn't support SHA-256 at this point. So there's really no point in putting DS records of type 1 in your parent zone anymore. So I actually encourage you to delete them. One DS record always has to match, though. This is where things can go wrong if you fail timing and you fail getting your parent updated properly as you're changing your keys. So in this case, this DS record had better match, the 257 key up above, or if you have multiple keys, it had better match at least one of those. So it's very critical that for validation to succeed, that DS record must match one DNS key in your zone at all times, and it should never, ever not be the case. This includes all records potentially in your resolver's caches, and not your resolver's caches, in the entire world's resolver's caches. If any resolver has a DNS key in its record, remember the entire set, and it remembers the entire set of keys, and it only has one key, and you've just changed the DS record in the parent, then that resolver, might go query the new DS record, but it'll still think it has the current DNS key set, and they won't align. Or the inverse of that, where it doesn't have the current DNS key record, but it has an old cached DS record, and it goes to ask for the new DNS keys. And if you remove the old one, there isn't a match there, then you'll end up in a real problem. If there's ever a case where the parent and child information in the cache doesn't match. Doesn't matter what's actually in the real records, in their caches. So how do you actually roll keys successfully? Well, this is ICANN's multi-step process for rolling the root zone's KSK. Fortunately, it's far more complex than you need to think about, but it shows you the level of thought that goes into potentially making changes in major world infrastructure with respect to rolling keys. And rolling keys in this case does mean, switching from one key signing key, one entry point key to another. So my rules to remember is, for updating information, this is the same slide as before, only mildly tweaked. Add new records, wait. Publish to the parent, wait. Remove old records, wait. Then remove your old records. So the third step there is remove old records at your parent. Some of those waits actually aren't needed, and some of that maximum wait time is not needed. You can go read the longer documentation for the exact timing if you want to narrow that down a little bit. But you should always remember that validating resolver caches can be in what I'm going to call a mixed state. They have some old records and some new records, and there is no way for you to assure that they'll all be updated at the same time. So you must assume that you need to wait long enough for all cached information to leave all resolvers everywhere on the planet before you continue at any particular point in a step. RFC 7583 has a lot of math and complex text that's well worth reading, but spend a little bit of time to get through a few pages, because it takes a little bit to think about it as you read these equations with lots of, things like how long does it take for information to propagate from, one place to another in a network and things like that. But they recommend really 3 different ways, but I'm only going to recommend 2 different ways of rolling your key signing key, rolling the thing that actually requires interaction with your parent. There's the double DS record, which is not the one that I think most people will use, but we'll cover first, which is you publish a new DS in your parent for a new key that you're not actually using yet. So you're only signing your stuff with an old key, but you publish the new DS record. So you end up with 2 DS records in your parent. And again, as I said, only one has to match. One has to match, but only one has to match. So as long as one of the DS records points to a key that you're currently using to sign everything, that's fine. And if you wait long enough, you can actually just switch the key on the fly. And then at some point later, after you wait again for all caches to get flushed, then you can remove the older DS from the parent. The double signing mechanism, which is using 2 DNS keys at the same time, is you publish the new key in advance and you wait. So you're using an old key, and then you add a second key, K new, and you wait for a long time. And then in the parent, you switch the DS record to point to K new. And then you wait. Again, that wait has to be not for what you think is right, but for what you think any resolver on the planet might actually, be caching your information. And that's based on both your TTL and your parent's TTL. And then you remove the old DNS key from your zone and you stop using it. The downside of the double signing is that you get longer. So both require some waiting. Both require, double DS requires that you have more parent interaction, right? You actually have to make changes to your parent twice at 2 different times. Whereas the double DNS key, you only have to do it once right in the middle step, but it requires bigger packets. You have more signatures and more keys to distribute it at any point. And that can be a problem because DNS can overgrow the packet size for UDP, the 1500 byte sort of, standard IP packet size. So you have to watch out for that and do some calculations. And for your sanity, don't ever change TTLs in the middle of this whole thing. If you're going to mess with TTLs, which we'll talk about in a minute, don't do it in the middle of this. You'll just hurt your head. Note that this does not work when you're rolling algorithms. When you're switching algorithms, that's a whole different process that I'm not going to get into today, because you end up needing to do double DS in order to get valid. Some validators require that a DS must match of every algorithm type that's published. So it adds some complexity. Some deployment recommendations on my side: use modern tools. Back when DNSSEC first came out, there was a lot of criticism that it was easy to break. It was true. You had to know what you were doing. It was true. You had to do your managing of your own keys, your own signing, your own rollovers. And the reason I got started in DNSSEC was actually to develop some tools to make that easier. These days, all software and pretty much all outsourced type services like Infoblox and other stuff can handle all of that for you. So it can handle all of that except for when you interact with your parent. All of these do the hard work, so you don't need to. Use modern algorithms. DS records, again, as I said earlier, SHA-256 should be the only type that signature you publish to your parent. And I think I'm guilty of some SHA-1s out there too, but it really doesn't help you, and any of them have to match. So if you have a SHA-1 algorithm out there and somebody actually figures out how to break SHA-1, in a DS record, which would be hard to do, but it's still much easier than 256. You might as well just drop SHA-1. Use elliptic curve algorithms. So the RSA keys have been phasing out rather rapidly, and we're doing a lot of measurements around that right now. I'm using algorithm 13, which is an elliptic curve based algorithm for all of the zones that I manage. And that is the one that is predominantly the most in use at the moment. There's 2 elliptic curve algorithms that are in use. There's some of the newest ones that you shouldn't use yet. The software is not yet out there to most of the world, but algorithm 13 is used by by resolvers in like 99.7 or 8% of the world. So it's really not a problem. Don't use NSEC 3. We're actually really trying to push people away from that unless you really have a need. .com does, you probably do not. And then monitor. You need to make sure that your parent and child records match. You should check those on a regular basis. You should have cron scripts out of cron or something like that to check them, because you need to know when they don't match, because they will at some point. That's just life. Things change. You need to check when things good. And then, how far out are your signatures still good for? Is something failing to sign for you? So I'm going to show you an example of that. These are actually two different graphs, one by monitoring at ISI that I do, and one that I actually have monitoring in my house, because we're all geeks and we have Grafana running in our house, right? I hope you all do. But so I have some vanity domains that I have checking, and you can see that these little dots on the far right hand side, right? Why are they there? I re-signed on this date all of my zones, and yet there's some dots down here that show the age of the signature lifetime is decreasing. And this is actually a manual pullover. And I'll talk about these in a second. If I look at isi.edu, we use info-blocks as well. So does UCDavis. It's actually signed on a regular basis. You can see once a day that it's re-signing. And then ARPA, which is a top-level TLD, also is doing a very regular kind of re-signing that's periodic. This periodic type thing really shows that automation is in play, and it's the way everybody should be doing it. I actually am going to convert my old scripts, that I built long before automation tools really existed, to be automated. But right now I'm actually still manually signing it because I'm a geek and I like self-control. But you can see that I actually did run into problems, right? These down spikes and these dots mean that there was a resolver out there that had cached information that if I didn't re-sign fast enough to wait for this whole cache to run out, I could run into just an equally likely problem where resolvers, just because I signed it a minute before the expiration date doesn't mean that people hadn't memorized that information. So Dave did want me to check about TTL recommendations. And so there's sort of a couple of schools of thought with respect to how long you should set your TTLs for DNSSEC or otherwise. Short TTLs give you the ability to change values really quickly. That's very important if you're doing load balancing and things like that, where you need to change address records, really frequently. Longer TTLs give you much better protection against outages. There's a paper at the bottom called "Cache Me If You Can: Effects of DNS Time to Live" that I'm a co-author on and was in IMC in 2018, where we sort of weigh these out. And it provides better protection against outages, and we prove that in both real world and in some simulated environments. It also provides faster long response time to end users, right? If you have really short TTLs, then that means that resolver is constantly going out to infrastructure to ask for updates. Whereas if it's long, it's going to remember it faster and it can respond to the end user much faster because it's answering out of its cache. My personal opinion is that generally your TTLs, unless you're doing load balancing or something, your TTLs should probably be greater than an hour. There's no reason for it to be shorter than that. And it should probably be less than a day. And I could go into all the thoughts behind this, but it really doesn't matter. The important thing is that this doesn't matter if it's just DNSSEC. I'm not just talking about DNSSEC. All of your records should probably subscribe to sort of this sort of thinking, at least, and policy. The only real thing for DNSSEC is that DNS key queries can cause fragmentation and cause more TCP connections. So you may want longer TTLs on DNS keys than other stuff, but generally I would still say never make them longer than a day. But that's my general recommendation. And there's a lot of backup behind that as well in terms of academic studies and engineering and things like that. DNSSEC gives you a lot of benefits as sort of a side slide of, once you have DNSSEC, you can do a lot of really cool things with it. You can do secured name lookups, of course, that's what we've been talking about. You can do secured SSH host key lookups. You can do secured mail-to-mail, server-to-server delivery. I'm a co-author of that specification, in fact. And then coming up in TLS 3 will be encrypted SNI, so that it encrypts sort of like the last part of a TLS connection, where you have to give the name of the web server that you're talking to the web server in clear text, and that won't be true in TLS 3, but it requires DNSSEC to trust it. There's a couple of resources down on the bottom that I'll show you screenshots of. The first is a statistics collection page that I and Victor Duchovny create based on scanning the internet daily for all of the DNSSEC stuff that's out there, and DNSVis is a troubleshooter. So this is sort of our exploratory page and what it looks like. If you put in UCDavis into our stats.dnssec.tools.org website, you'll get, that UCDavis is actually using SHA-1. It's a warning. It's not, a critical thing. And that you're not actually using secured mail, which requires DNSSEC. Outlook is actually going to start providing that soon. So it's actually quite possible you'll actually get that almost for free, if not for free, depending on how they implement it. Supposedly it's on their roadmap. DNSvisnet helps you diagram what's going on. You can see here's all the key changes in how things point that I talked about earlier. You can see it gives you a warning too for the algorithm being, the digest algorithm 1, the SHA-1 algorithm being old, pointing to the same key. But you can see both DS records are pointing to the key. And it's a great thing to do to check if your current data is up to date. Note that it actually caches information too, but there's a button saying, no, please go refresh new data because I just published a whole bunch of new stuff. So you can check it. So with that, I tried to leave some time for questions. There's a bunch of slides there. My email address is on there if you want to write me as well. But if you want to do follow along stuff, there's 2 hour-and-a-half, 2-hour presentations called DNS Deep Dives that are parts 1 and 2. Myself and 2 other IETF colleagues gave those to the IETF, and they're on YouTube. They go into, you'll see a lot of repeated material from the slides that I did today because I pulled some out of that one to give this one. And then just for a funny one, A Cat Explains DNS is kind of fun to watch somebody dressed up as a cat driving around in a car explaining how DNS works. So if you want entertainment, that last one's for you. With that, I will turn it over to questions. And Dave and others to help me with questions.
Yes, so thanks, Wes. I don't see any hands up, but
Everybody fell asleep, possibly.
or you were very thorough. And in terms of the questions, there were a couple that came up in chat, and I think those were answered. So what, actually, one of our security guys asked about Let's Encrypt around DNS, root DNS checks. Do you know anything about that and have any thoughts about how they Let's Encrypt works? Are you familiar with that?
Well, I am some. I mean, Let's Encrypt actually is now sort of a standardized thing out of the ACME working group in the IETF. And then how it works, that is. They do a number of things because, there's a huge number of domains that aren't signed with DNS Sec. I don't know if they actually do DNS Sec validation. That's actually a good question. I know they didn't for a long time. They might now. But they do vantage points from multiple places around the world, which would make it really hard to cache poison all the resolvers that their infrastructure are using. So their approach to security there is, I'm going to ask DNS questions and do TCP connections to your web server from around the planet in multiple places, making it very hard to thwart. So that's their security model for dealing with trusting that they got to your right web server and your right web key.
And then the other comments were, we got lots of thanks for a great presentation and +1s and thumbs up. I don't see, I think that's a testimonial to how thorough and comprehensive you were.
I will answer one question that I expected to come up that I didn't put a slide in, which is if I go back to, I talked about what the right length for TTLs were. I didn't talk about what the right length for signature times were, right? So these last 2 is how long should you have a signature length for? And my answer to my own question is probably 7 to 14 days if you're using anything automated. There's no reason to do something longer than that. If you're doing manual stuff, then you might consider 30 days or something, and you should re-sign it in at least half that interval. You should re-sign on a much more regular basis. But generally speaking, signature lengths don't need to be that long. It's not super dangerous to have very long ones if you are quite confident that that information will never change. Because it's so long, any malicious actors can replay that data because the signature will be valid for a very long time. And that, there's very little reason why that might be a valid source of attack for most people, but do consider those signature lengths, especially if you're doing infrastructure changes on a frequent basis or changing, addresses or name servers or mail servers or something on a frequent basis, or have roaming users that you're putting into assigned zones. But
so Wes, that leads to a question actually now that I have. We talked about TTLs and you suggest most of them being less than 1 day across the board for all TTLs. Does that mean then also that your zone signing key should re-sign DNS, the DNS Sec, your zones daily?
Good question. So those are somewhat unrelated in terms of length. So the TTL is how long a resolver can keep it. There's nothing wrong with having a signature length that is 7 days, valid. and they still need to keep asking you for it every hour, right? There's nothing wrong with that, or every day. The important takeaways are they're two totally different things to consider, right? One is how often you want your client to come back and ask you for information, regardless of whether you're going to change it or not. And the other is how long are you going to, be changing that data, and how automated is your infrastructure to do that re-signing in order to, to decrease that signature length time. So they're all engineering decisions in terms of how important is it that you keep a shorter security lifespan on that data.
So what I should have asked was, since you're recommending that the DNS Sec signature end date be a week, that we have to re-sign the zones once a week at least.
Yeah, and so I would always recommend signing at least half that time. So I would say 3.5 days. But the reality is, if you're using automated software or automated outsourced systems, regardless of whether it's bind or infoblox or not, or any of those things, they're set up really to do it daily in the first place. And so there's no downside to re-signing daily. So if you can automate it and re-sign frequently, in the same way that Let's Encrypt has you, updating keys every 3 months, right? Their goal of that, the whole reason for them doing it every 3 months was to force you to automate, right? If you have to re-sign every day, I guarantee you're going to automate, and that's a good thing.
All right, good stuff. And then we do have a couple questions. Chip, you have your hand up.
Okay, yeah, thanks. So one thing that's on my mind, and I don't think it's an issue, but you're talking about the DNS chain, or DNSSEC chain, and we have a situation on campus where it eventually gets to a level where we delegate out authority for the DNS records below that point, like subdomain or something.
Right.
And so if we have the DNSSEC, set up within our control at the point that it leaves to that external resolver, that doesn't break anything, right? Or
Nope.
Does it just say, okay, I'm gonna stop looking for signed records at that point?
Yeah, excellent question. I was sort of waiting for that one too. So thank you for bringing it up, because let's say that www is actually a subdomain of UCDavis rather than a separate record. If there is no DS record in UCDavis for www, it proves, because remember that one of the things that DNSSEC gives you is the proof of non-existence, right? UCDavis with its signatures is not only able to prove that a name doesn't exist, but a type that goes along with it doesn't exist. So UCDavis will actually have a signed object that says there is no DS record for www, or if UCDavis wasn't signed, there is no DS record for UCDavis, at which point the resolver goes, okay, all bets are off. There's no DNSSEC below this point. I've just got to trust stuff.
Got it. Thank you.
Yeah, good question, Chip. Then other questions have come up. One was from Justin Woods, and it has to do with the graphics early on with all the lines. And his question is, did you draw those all yourself, or
Oh, no.
for that?
No, that is GraphViz at work. GraphViz is an awesome drawing package. I think many people are familiar with it. It's way back in the beginning. That actually was software I wrote just to demonstrate. So I actually was parsing TCP dump or T-Shark output, I forget which, to create all of the records, and then actually draw that. It's old enough that it was written in Perl, to give you a hint of its age. So
I think that's it for all the questions, and we are almost. Oh wait, one last one. Any early warning techniques that you're using to monitor resolution fidelity?
So yeah, I mean that graph that I showed toward the end, which is looking for outages. We have daily queries, every 10-minute queries to all of our infrastructure to make sure everything is up. And if something doesn't go, if something's not up, then I get notified immediately. And so I do the same thing for DNSSEC related signed zones of, go query and make sure that it's returning, up to date recent information. You can use RIPE's Atlas if you want to query from sort of around the planet in order to figure out what people have in their caches and things like that. That actually, can query from 4,000 different, places around the planet. That's a really useful utility.
All right, great. That brings us to time. I'll just add that this will be sort of slightly edited and posted to YouTube along with Wes's other presentations. And if you can't find it just by a search, they can search for your name on YouTube. Would it bring it up?
Yeah, it would. And the ISI page that I linked to at the end, if you search for ISI in Hardaker, there's actually a whole publications list that also includes presentations. And in that is a list of YouTube links, and that includes those two things. So,
Great. And if you can't find it there, send Wes an email or send me an email and I'll
yeah,
point to the link.
absolutely.
Okay. And thank you very much, Wes, for doing this for us. I owe you a whiskey.
Fair enough. All right. Bye, everybody. Thanks for coming.